We're going to do a more careful job of figuring out everything we need to save away, and when we do procedure calls, we're going to try to solve all these problems and come up with a nice airtight convention we're going to use. And it's actually reasonably straightforward, but there are a lot of details to take care of. So that straightforward does not necessarily mean simple in the sense of I can tell it to you in one sentence. We're actually going to have a bunch of conventions. And in a couple slides, I'll lay them out for you explicitly. But just to make our little laundry list, right, we need to have some way of passing arguments. And 1 argument, 2 arguments, 17 arguments, 22 arguments. Most languages allow procedures to have as many arguments as you want. And some languages even allow procedures to have variable numbers of arguments. Like printf in C, you can pass in a simple string or a string with lots of other values. And the number of values that you pass in, you can write 3 values to be printed by a printf or 17 values. It all depends what the format string is. Right? So we're going to have to figure out a convention for passing arguments that doesn't key on if you only have at most 5. We're going to have to allow more than 5. A convention for the return address and a convention for returning the results back to the caller. Notice, by the way, that in most languages you can put an expression in for an argument. So here I'm calling the function sign on a plus b. The expectation is the compiler will compute the value of a plus b and then pass the result of the sum. It's not actually passing little pieces of code in. It's just the code there is just a way of telling the compiler, compute this expression, and the value of that expression is what gets passed in as an argument. Inside the procedure, we may have complicated expressions. And in fact, if there's a nested procedure call, we may have to save a computation that we're halfway through, the temporary result. We may have to save it somewhere. We may have local variables, and we haven't talked really at all about, if we have a local variable, where should that go? But we'll solve all these problems in a second. The point I'm trying to make is when I do a procedure call, there's a whole list of storage requirements that I need. Places to put the arguments, places to remember where I'm supposed to go to when I'm done executing the procedure, places for temporary results, places for local variables. Altogether, I can make a long laundry list of everything Factorial will need to be, to get its job done. And collectively, we're going to call these an activation record. It's a collection of storage that we need. Every time I make a call to Factorial, this storage has to be put somewhere. Okay. And in fact, when I make a call to Factorial, for instance, fact of 3, you can see that somewhere along the way, it will make a recursive call to fact of 2. And fact of 2 has that same laundry list of things it needs to save, all of which will be different than the values that are being saved for fact of 3. So there's sort of this notion of this accumulation of these activation records. Right? As I continue my calls, I'm getting more and more and more activation records sort of being stacked up somewhere. And I use the word stack very carefully because that will give us it gives us a hint about the data structure we're going to use to hold those activation records. And then finally, when I start returning, when I'm finally done with the procedure, I stick the answer into R0, and then what I'm going to do is I can get rid of that activation record. I'm done. Fact of 0 is done now. Fact of 0 has finished its job completely. It's put its answer into R0. That's the residue of its life. And now we take the corpse and we can say, okay, all that other storage, that the temporary variables, the local variables, you're done. Those can be recycled. We can return those to ashes to ashes. So once we exit that procedure call, we no longer need its activation record. And in fact, if you look carefully about when activation records are created and destroyed, they follow a very simple discipline. Every time you make a nested procedure call, you add a new activation record, but then you have to return from the nested procedure calls in the same order that you called them. So you might do call, 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 return, return, call, return, call, return. But you can sort of see that at any moment when we return, we get rid of the topmost activation record in the stack of activation records that we have. So imagine each one of these books records all the information that we want for a particular invocation of a procedure. Its argument, where to return to, any local variables that are just for that procedure call. Those are all written in pages of each one of these volumes. And every time we do another nested procedure call, we need to add new activation records. And so this notion that this is sort of a last in, first out data structure. If it helps you to think of it this way, think of it as a napkin holder. You can stuff napkins into the top and you can take them out one by one, but we're always ever dealing with, if you will, the top napkin. Okay. And at some point I start returning, and what we're seeing now is the stack is going down. So the stack is a data structure, and in fact, all of your laptops, every procedure that runs has its own stack, and all the compiled languages, C and Java and Python, or I don't mean compile, all the languages which implement procedure calls all have this notion of an activation record that's created for each procedure call, and it stores those activations in a last in, first out data structure that we call the stack.